So the topic of today's video is phase lines, aka ropes, and just to add a little graphic here, we got a little man climbing up on a rope, which you'll understand later when we talk about what a phase line is. But so at this point, you've gotten pretty good at creating slope fields, and hopefully you've got a pretty good idea of what the slope fields tell you about the solutions or the possible solutions to a differential equation. And I also would assume that you've discovered the tedium of drawing slope lines by hand. And slope lines are great if we have the technology to create them for us, because they, in a quick flash, the technology can create them, and then we can look at them and really get some good ideas of long-term behavior of the possible functions dependent upon the initial condition. So slope fields are a really good tool, but they're not well, they just take a lot of work to create by hand. So phase lines is kind of a shortcut method that they're not as thorough and as informative as a slope line is possibly, but we can definitely use them to get at some of the same ideas as a slope field. Now, one thing to point out is that we only can use phase lines with autonomous differential equations. Which, remember, autonomous differential equation means that the derivative is defined in terms of only the dependent variable. It does not include, so like in this case we have dy dx is equal to 1 minus y times y. Notice there's no x involved in the defining of the derivative. So that is an autonomous equation, and that enables us to use phase lines. So phase lines are based on an idea that we talked about, well, actually I guess in class a little bit, but I pointed it out in the videos too. But if we hop over here to a slope field of this same graph, same equation, so it's a differential equation is 1 minus y in parentheses times y. And here's the slope field. And when it's an autonomous equation, we notice that within the slope field, there's vertical lines, or every horizontal line has the same slope. So as you run along, for example, y equals, what is that about? Looks like about an eighth or something. Y equals an eighth, you can see all those little slopes are the same, they're parallel to each other, right? And if you run along any horizontal line, all the slopes are the same. So if we know just one of these lines, then we know all of these lines, because if I know this slope, then I know all of those slopes, and if I know this slope, I know all of those slopes. So recognizing that, we can represent the slope with just a single line, essentially. Now again, it doesn't give us as detailed of information, but it gives us the idea of the overall trend. So generally what we do is we just take the y-axis. Now on this one there isn't anything on the y-axis, but we can get the idea because they're the same all the way across, right? And this also relies heavily on the This relies heavily on the equilibrium solutions. So we've talked about those a fair amount. So equilibrium solutions is where the derivative is, where the expression is of the derivative is equal to 0, and those always show up on the slope field quite nicely. You can see there's one here at 1 where all the lines are flat, and then there's another one at 0. They're not drawn in, but we know there's one at 0 because if you look up here, what makes this expression 0 is if we plug in a 1 for y, 1 minus y is 0. If we plug in a 0 for y, then obviously the overall expression is 0. So the two equilibrium solutions would be y of t equals 1 and y of t equals 0. So now the other solutions, of course, are not going to be that simple. We always refer to as the equilibrium solutions, kind of the simple ones or the basic ones. And here's some examples of some other solutions. And so what the phase line is going to do is going to allow me to pick up some general trends of what happens. If I know the initial condition, and you can see on these that I drew, I gave you the initial condition, right? See those little initial conditions there? So if you know the initial condition, then from the slope field we can draw it. But what our goal is for this video is to actually be able to roughly sketch the graph, or the solution, with just one line. So one line of this. That's basically what a phase line is. Okay, and sometimes we refer to these phase lines as the man climbing a rope function. So if we go back over here, where was it? Right there. So that's why I have this little drawing here, because what we're going to do is we're going to take essentially the y-axis, right? And we'll put a little x-axis in there just for reference. No, actually, I think I'll leave it off. We'll just put a little mark for y equals 0. And the first thing you do on the phase line is you put in the equilibrium solutions. So we know there's the equilibrium solution at y equals 0 and another one at y equals 1. And we put a little dot on there. So basically what happens, we know that at that dot, the derivative is 0. So one way to refer to phase lines is you think about a man climbing a rope. And he climbs the rope. His speed with which he climbs the rope is determined by this derivative. So just so you can picture that a little bit better, I'm going to hop over here and show you a man climbing a rope. So you can see that in this case he's just kind of slowly climbing up the rope. This wasn't really necessary, but I thought you might enjoy a little break from the math. Okay, but now let's go back to what we were talking about. So you picture the man climbing the rope, and so basically what this phase line is that if the man was sitting here, his speed is 0. If the man started here, his speed was 0, which means he'd never go up or down. He would just stay at y equals 1. And that is, if you go to the to our slope field, you could see if the initial condition was at 0, the initial condition was 0, then because the slope is 0 there, if you let time run, he's just going to stay at the same height the whole time. He doesn't move, okay? And that's also true of 1. If we were to, if the man was to start at a height of 1, and the derivative tells us how fast he's climbing, so at y equals 1, the derivative is 0, which means he's not climbing at all, so he would just stay at that height. Okay, so now, what happens if he doesn't start at one of those points? So we'll go back over here. And so let's say he started at, for example, 0.5. And let's say our initial condition was y of 0 equals 0.5. Okay? Well, if we look at the slope field real quick, if he starts at 0.5, you can see that right down here, a little bit below 0.5, the slope is going up very slightly, and right above 0.5, it's going up even steeper. Notice there's no going down anywhere. So if he starts right here, his velocity is positive, or in other words, how fast he's moving up and down the rope, is positive, which means he would be climbing up. So, and that's true anywhere between 0 and 1. You can tell that. Now, we can also tell that if we go back to the equation and look at it. If I plug in a number between 0 and 1, no matter what it is, as long as it's between 0 and 1, this will be positive. Because if I plug in anything less than 1 or bigger than 0, that will be positive. And of course, if I'm plugging in something between 0 and 1, it's positive. So we're going to have a positive times a positive. So anything between 0 and 1 is going to produce a positive derivative, which tells the climber that he should go up. So if he starts anywhere, if my initial condition is y equals something between 0 and 1, then as time goes forward, he's going to go up. Okay? Now, what if he starts above y equals 1? So then let's go back and look at the slope field again. You can see that as anything above y equals 1, the slopes are negative. All these little lines here have a negative slope, and they're really steep up here and less steep down here. But there isn't a positive slope anywhere. So again, if we go back and look at the equation, that would make sense, because if I plug in a number bigger than 1, then this part is going to be negative, right? As long as y is bigger than 1, this will be negative. But since I'm picking something bigger than 1, the y will be positive, so this will be a negative times a positive. So anything bigger, any y bigger than 1 is going to produce a negative slope, which means if the man starts up here somewhere, then he is going to go down. Okay? So if he starts between 0 and 1, he's going to be going up. If he starts above 1, he's going to be going down as time progresses. Okay? And again, this should illustrate kind of what the slope field is telling us. So if my initial condition started right there, you can see the slope field is telling me as I go to the right to go down and get closer and closer to that horizontal line. And the earlier one was said if he starts at 0.5, notice the slope line says to go up, and he'll get closer and closer to, again, that horizontal line at y equals 1. Notice if he goes backwards, of course, the opposite thing happens, because just like if you think about a linear equation, if you have a positive slope, if I go forward, I go up, but if I go backwards in time, then I would go down. So this, on the slope, on the phase line, these little directional arrows are telling us what would happen if time moves forward, if the independent variable moves forward. Okay? So then one more, we're not even going to look at the slope field this time, we're going to look at just the equation. If my y is less than 0, so if I start at a y less than 0, then notice if y is less than 0, then this is going to be 1 minus a negative y, which would turn it into positive, right? So that would be positive. And if I plug in a negative number in here, that would be negative. So we're multiplying together and we get negative. So that means it should be going down. Now let's check the slope field and see if they confirm that. And sure enough, the slopes are negative down there too. So the only place the slopes are positive is between the two equilibrium solutions. And then above the top one, it's going down, and below the bottom one, it's going down. So now, if we go back and look at what we've done, so this is a phase line that we just drew here. And again, if you want to think of it like the man climbing the rope, the initial condition tells me where to start on the rope, and then the arrows tell me which way to go as time progresses. So if I'm thinking about starting on the y-axis, that's, y of 0 equals 0.5. So if I start at 0.5, and as time goes forward, this says that my man should climb upwards. So as time goes forward, he's going to go up. Now, how fast does he go up? Does he shoot up, or does he go like that? We don't really know just by looking at the phase line. Obviously, if we look at the slope fields, we can tell, but we can't tell how steep to go except for this. We know that as you get close to an equilibrium solution, the steepness of your slope is less. Or if we think about the man climbing the rope, as he gets close to a equilibrium point, that's what we call these things, on the rope, if he gets close to an equilibrium point, he slows down. So he's going to be going up the whole time in here, but as he gets close to the equilibrium point, he would slow down. So knowing that, as I go forward, I'm going to take off, but I'm going to slow down as I get close to it. And likewise, if I was to go backwards in time, then obviously a positive slope. As you go backwards, you would go down, but he also has a equilibrium point below him, so his speed is going to decrease. So again, this is the idea. I can look at this phase line and I can see that if I have an initial condition of y of 0 equals 0.5, and just looking at that little arrow, it tells me that as I go forward, I go up and slow down if I'm getting close to an equilibrium point. If there is no equilibrium point above me, then I can just shoot up off into space, right? And so let's look at another one. Let's say that I would have started at, we'll do a different color here. Let's say my initial condition is y of 0 equals 3. Well, then I go up to 2, 3, that'd be starting right here. And again, this black arrow tells me I should go down as I go to the right. So as time progresses, the mountain or the rope climber goes down. And likewise, when I get close to a equilibrium point, I slow down. So he's going to come down like this and slow down as he gets close. And if I go backwards in time, a negative slope means that I would go up. So, and notice there's no equilibrium point above me. So in this case, he's just going to head up to space. And so let's hop back over here real quick. Sorry about the hopping back and forth. And you can see, oh shoot, I didn't do any of the anything above. Let's, but you can see that if I did do one above, like what was the we did 3, right? So if I started right there, you can see that it's going really fast up on the left and slowing down as it gets close to the equilibrium point. So you can see that graph that we just did, and also you can look in here and see the type of solutions that show up between the between the equilibrium points. Okay, so that's building a phase line and using a phase line. Let's do another example just for fun. So let's say that I have dy dx is equal, and this time we're not even going to look at the slope field. Dy dx equals 2 minus y times sine of y. Okay, so again, if we're building a phase line, the first thing we're going to do is find the equilibrium points. So in other words, when does this thing equal 0? When does 2 minus y times sine y equal 0? Okay, so we know that when y equals 2, that's 1 point, but we also know that sine hits 0 a bunch of times. In fact, if we think about the sine curve, it actually, every pi, it hits there. So we have a very equilibrium point at every n pi, where n is an element of the integers. So if we just start out, we're not going to draw all of those, of course, but here's my little phase line. I'm going to start out at y equals 2, for example. That's one of them. But then there's also one at, if I put in 0 for n, that would be at 0. So we'll go down here at 0, and that's a equilibrium point. We got another one at pi, which is 3.14, so that'd be right about there. We'll say y equals pi. There'll be another one at 2 pi, so that would be, what, 1, 2, 3, 4, 5, 6, and a little bit. So right about there, y equals 2 pi. So you can see we're just putting in all the equilibrium points. And then we got to go in and draw the arrows between those so we know what they look like. So at this point, I would suggest that you pause the video for a minute and see if you can figure out where to put the arrow, or which direction to put the arrows between the equilibrium points. So we need an arrow in there, and in there, and there, and then below that for now. All right, so go ahead and pause the video and try that. Okay, so while you guys are pausing, I paused the video and put the arrows in so you can check yourself so you don't wreck yourself. You can see the little green arrows, so you should be able to determine which way the arrows are going based on when this is positive and when this is negative. So that's so So that's the phase lines. You should be able to draw them and be able to, once you've drawn them, know what they tell you about the possible solutions based on initial conditions. All right.